Okay, welcome to the third day of the Bootstrap School, and we will continue with the third lecture by Edward Witten.
Thank you. Well, this lecture, as you can see, is on a somewhat different topic, quantum field theory and curved spacetime. And I hope it'll be a more relaxed lecture than the first two. What I'll be explaining is kind of elementary. I decided to explain it because I found that things that, well, I thought maybe some relatively elementary things are worth explaining. But I'm also worried about disappointing you because the topic, why does quantum field theory and curved spacetime make sense, is kind of bigger than what I'll explain in this lecture. I'm really only going to talk explicitly about free field theories and curved spacetime. And I won't give proofs, but I'll try to make it obvious what should be true and how to think about it. I think it's obvious intuitively that once the free theory is well-defined, there's no problem in perturbation theory. And although it's less obvious, I expect the same to be true for strongly coupled theories without a classical limit. In other words, I expect the picture to be the same for all quantum field theories, but it's less obvious how you'd prove that. So we start with the free theory based on an action that, for example, might be the action for a free scalar field, which I wrote will be in Lorentz signature today. So I wrote it for a Lorentz signature metric of signature minus plus plus plus. Now, if the background metric G is time independent, there's no difficulty. We just construct a complete basis of C-number solutions of the field equation of phi. And then we expand in modes of positive and negative frequency. And we introduce a ground state omega of lowest energy annihilated by the annihilation operators. Then we make a Fock space of all states that you can get back to know the ground state with finitely many creation operators. That Fock space is what's called a pre-Hilbert space. That's just a fancy way to say that it obeys all axioms of a Hilbert space, except it's not complete. So complete would mean if you have a sequence of states such that the norm of their difference is getting smaller and smaller fast enough, they should have a limit. Technically, a Cauchy sequence should converge. If you take a Fock space, it's not a Hilbert space because you could, for example, add with a very, very small coefficient a state with n particles. The sum of such states should converge if the coefficients are sufficiently small for large n, but it doesn't actually converge to a Fock space vector. So when you have a pre-Hilbert space, you usually want to make a completion of it to get a Hilbert space. So what we do if we have a time-independent metric is we expand in creation and annihilation operators. Then we define a Fock space with finite many creation operators acting on the vacuum. And the Hilbert space closure of that is the Hilbert space of our quantum field theory. Well, we did more than just construct a Hilbert space. We constructed a Hilbert space with the preferred state psi, the ground state, that minimizes the energy. In other words, in a time-dependent background, there's a conserved energy E. I'm not sure why I called it psi here and omega here, but anyway, omega, the ground state, was the state of lowest E. Well, in the more general case of the time-dependent background, there's no conserved energy, and you should not expect to find a distinguished state in the Hilbert space. So this is a point that has occasionally caused confusion where people ask, what's the vacuum or blah, blah. But you shouldn't expect to have a vacuum or anything you'd call a preferred state in a when you're doing quantum field theory in a time-dependent background. So we'll have to construct a Hilbert space H without having a distinguished state in it. But that in itself isn't a problem. You all learned to do this when you studied non-relativistic quantum mechanics. For example, consider a free particle with position and momentum coordinates, x and p, where I'm in d dimensions, so x and p are d vectors, and with the usual commutators. When you studied non-relativistic quantum mechanics, you learned how to associate to this data a Hilbert space H that has no preferred state. For example, this Hilbert space could be a space of L2 functions of x. They really are more properly half densities rather than functions. If your textbook called them functions, that was because they assumed you had a known measure. But more intrinsically, if you didn't have a known measure, your functions are really half densities, which is just a fancy way to say something whose square is a measure. But if that's confused you, never mind, it won't be important in the lecture. So you could use a Hilbert space of L2 functions of X or a Hilbert space of L2 functions of P. Or you could use coherent state quantization and work with functions of X plus IP, which I'll call Z, or with X plus tau P, where in tau is positive. And there are more general versions that some quantum mechanics books might have explained, where you take functions of half of the X's and P's in more general fashions. All these constructions are actually equivalent by Fourier transforms and more general canonical transformations that might have been explained in your course on quantum mechanics. And they can be combined and slightly generalized in different ways. But regardless of how you do it, there's no preferred state in this Hilbert space without more information. So you're all completely familiar with quantum mechanical Hilbert spaces that are not born with any preferred state, even though it sometimes gets forgotten when people want to think about quantum field theory in curved spacetime. Now, this slide is a digression in the context of the lecture, but there's a remark I want to make. It's important here that the classical phase space was not an abstract symplectic manifold, but has an additional structure. We know what functions on the phase space are linear functions, namely X and P. So the problem of quantizing an abstract phase space without knowing what are linear functions is completely different and highly problematical. But it's not relevant today because in free field theory, there is a preferred set of linear functions on the phase space, namely the elementary field variables phi of T and X. So there's a completely different problem of quantizing an abstract classical phase space, but it's not relevant today, and I won't tell you anything about that problem. Now, if you go back to the Hilbert space H where you quantize X and P, of course, there might be a preferred state. For example, with one X and one P, you might have a harmonic oscillator Hamiltonian. If such a Hamiltonian is present, it tells you how to pick a preferred state, which is its ground state. And of course, that depends on the specific Hamiltonian. But as long as there are only finitely many variables, we can define the Hilbert space for quantization of X and P without knowing anything else, like what's the Hamiltonian. So there's no problem to define a Hilbert space with no information about picking a preferred state. And that works fine for bosons with the notion of linear function on phase space, as long as the number of X's and P's is finite. But in quantum field theory, the number is infinite and there's more to say. So let's practice with something simpler, an infinite collection of qubits. You can think of a qubit as a spin half particle. And I arranged a few at random on the slide to suggest that there's no structure at all except we have an infinite set of qubits. So here's a question. Does the Hilbert space of a countably infinite collection of qubits have countable or uncountable dimension? I hope you can see that, okay, that's like asking how many real numbers there are between 0 and 1. Think of a qubit as having two states, 0 and 1. So you're describing the decimal expansion of a number that's between 0 and 1. So if you ask this question with absolutely no structure, the answer is the Hilbert space has uncountable dimension. The Hilbert space H hat that literally describes all possible states of an infinite collection of qubits definitely has an uncountable dimension. But it's never, I wasn't sure whether I almost never or never. It's never useful to do physics in a Hilbert space of uncountable dimension. Almost always anything useful can be stated in a Hilbert space of countable dimension. Hilbert spaces of countable dimension, just as terminology, are called separable. I'm pretty confident that none of you have ever seen any physics done in a non-separable Hilbert space. Now, what we should do depends on what we're interested in. To get anywhere, first of all, we should have a class of operators on this big Hilbert space that we regard as sensible physical observables. Then we can look for a separable or countable dimension subspace of the ridiculously big Hilbert space H hat that's big enough to realize the algebra of physical observables and to describe the states we care about. So there are two ingredients here. What class of observables do we care about and what class of states do we care about? You can't specify them independently because the states, the observables we care about have to be able to act on the states we care about. In the case of the qubits, you might decide that you care about the single qubit operators. And then you would make an algebra of operators. So first of all, on the nth qubit, apart from the identity, you have the spin operators, the components of sigma x, sigma y, and sigma z for the nth qubit. So you can make an algebra A0 that consists of all polynomials and the Pauli spin operators of all the qubits. So A0 consists of finite linear combinations of components of single qubit operators for different spins. I've called this A0 because usually you want to take some kind of completion A0 to get the algebra of physical observables. Because just as for states, also for operators, right, here we defined the ones that act on only n qubits, but usually for finite n, but usually we want to allow ones that act on an arbitrary number of qubits, but with very, very small coefficients, with some kind of convergence. But you can't discuss the completion of A0 to get A without deciding what kind of states you're interested in it acting on. As we'll see in a second, the little algebra A0, we can just define it once and for all, but to complete it, we'll have to have a class of states. So as an example of what you might be interested in, maybe you know that the qubits are almost all in the spin-up state along the z-axis. Then you might decide that the physical Hilbert space should at least contain the vector omega, where all spins are up. And since you want to have A0 as an algebra of observables, you then have to include all states acting with A0 on omega. Well, when you act with A0 on omega, since A0 contains all the operators that act on a finite set of qubits, you get all states in which all but finitely many qubits are in this state up, spin up along Z. So states of this kind make a separable, that means countable dimension, pre-Hilbert space H0. You can take its Hilbert space completion H, which is also separable, and it admits the action of A0. Moreover, you can now complete A0. And what completing A0 means is that you say that sequences converge if all their matrix elements converge for vectors in H. We had to know what H was to state that condition. But now that we have a Hilbert space, we can take a completion of the operators. Once again, what I'm defining is called the weak completion. You say that a sequence of operators converges if all the matrix elements converge for states in H. But that gives an answer that depends on H. And once we've decided what H is, we can take the completion of the algebra. And in this case, that gives a von Neumann algebra of type 1, all bounded operators on a separable Hilbert space, namely the Hilbert space H. So that was an answer that made sense and tells us how to do, if the states we're interested in are states where almost all the spins are up, in the Hilbert space sense. And that's not literally all but finitely many spins are up, but every state can be approximated in the Hilbert space sense by states where almost all but finitely many spins are up. If that's what you're interested in, then you can, that tells you how to complete your algebra and also what Hilbert space you want. Now, I'm sure it's clear nothing was special about the state we started with where all the spins are up. We could have started with any state in the uncountable Hilbert space that we like for any reason. Then we define a pre-Hilbert space H0 by including all states obtained by acting on psi with a small algebra, which means flipping any finite set of spins in any fashion. Then we take a Hilbert space completion of H0. That gives us a Hilbert space H in which A0 acts. And then taking a closure of A0 gives the algebra of observables in this Hilbert space. So we can get all kinds of things depending on what we're interested in. I kind of already said this, but let me explain in more detail why the algebra depends on the Hilbert space. When we say that a sequence of operators converges, we mean that all limits of matrix elements exist for all states in the Hilbert space. This criterion depends on the Hilbert space. So although the small algebra A0 was universal, its completion is not. If the sequences all converge, we define a limit operator A, whose matrix elements are the limits of the matrix elements. That defines an algebra that acts on H. And in this construction, it's going to be the type 1 von Neumann algebra of all bounded operators on H. But later, by such weak limits, we'll get non-isomorphic algebras, strange algebras of the kind that arise for a local region in quantum field theory. Now, so far we were considering abstract infinite collections of qubits, so we could only describe relatively stupid states. But to make it more physical, we could arrange our countable set of qubits on a lattice, like the two-dimensional lattice in this picture, and we might have a lattice Hamiltonian. For example, Heisenberg spin Hamiltonian. Then we could take psi to be the ground state of the Hamiltonian. And starting with this psi, we would then construct a separable Hilbert space on which all the elementary spin operators act. And we would complete it to get a good algebra for that Hilbert space. But the Hilbert space we would get would depend on the lattice Hamiltonian we chose. Now, suppose we construct a Hilbert space H psi from some input state psi, and a Hilbert space H psi prime, starting with a different input state psi prime. So H psi and H psi prime are both subspaces of the ridiculous, uncountable, non-separable Hilbert space H hat, because psi and psi prime were both vectors in H hat. We did everything in this ridiculously big Hilbert space, so the two small Hilbert spaces we got are subspaces of the same big one. Are they the same subspace? Well, obviously, for them to be the same subspace, psi prime has got to be in the Hilbert space H psi that you created starting from psi. That's a necessary condition. It's actually also sufficient. You see, the definition of H psi was that states in H psi can be approximated by states of the form O psi, where O is in the small algebra. So if psi prime is in H psi, it means psi prime can be approximated by states O psi. But then H psi prime, by definition, consists of states that can be approximated by O prime psi prime, again with O prime in the small algebra. But if you have a state that can be approximated as O prime psi prime, where psi prime can be approximated as O psi, that means your state can be approximated as O prime O psi. O prime and O were in the small algebra, and the small algebra is an algebra, so O prime O is still in the small algebra. So anything that can be approximated as O prime O is actually in H psi. So we've proved that if psi prime is in H psi, then the whole Hilbert space constructed from psi prime is in H psi. And conversely, you can show that if psi prime can be approximated as O psi, then psi can be approximated as O prime psi prime. In other words, if you can approximate psi prime by flipping finite many spins from psi, then you can do the opposite and approximate psi by flipping finite many spins in psi prime. So the same argument shows that H psi is contained in H psi prime. So as long as the seed vectors are in each other as Hilbert spaces, the two Hilbert spaces are actually the same. Now let's discuss something a little closer to field theory. We'll consider an infinite sequence of pairs of canonical variables, x1, p1, x2, p2, and so on. So the kth pair can be quantized to give Hilbert space H sub k. And for this, we don't need to know anything about a preferred vector. But if we want to describe all the states in all the HK, we have to define a Hilbert space H hat, which would be the complete tensor product of all these. And it again has an uncountably infinite dimension. So it's much too big for any reasonable physics. But if we're given a state psi that for some reason we like, we can proceed as before. We define an algebra A0 that consists of all polynomials in the x's and p's. We define a pre-Hilbert space H0 that consists of all states that can be made from psi by acting with A0. And as usual, we complete this to a Hilbert space H. And then we also complete A0 to an algebra A. In this case, we might have wanted to take bounded functions of x and p's, as I was asked just before the beginning of the lecture, before trying to take the completion. So that would be probably technically a better thing to do. The type of completion I explained before wouldn't work well for unbounded operators. So this last sentence, well, in writing it, I skipped replacing the polynomials in x and p by bounded functions of those polynomials. So here's a simple example. So what it's an example of is this. To get from this ridiculously big Hilbert space to one of a sensible size, we could do if we had a vector that for some reason we like. So an example would be a vector that's a tensor product of a vector psi k in each hk. For example, for each K, we might have had a harmonic oscillator Hamiltonian. Then we pick the ground state in each one. We can assume that the psi Ks and therefore also psi are normalized. And we would construct a Hilbert space H psi starting with psi. On the other hand, consider another state of the same kind, where again we assume that chi, k, and chi to be normalized. Is the Hilbert space H chi the same as H psi? Well, let's try to take the inner product between the two states. So let Cn be the inner product of chi n with psi n. After possibly changing the phases of the chi n, we can assume that Cn is non-negative. So then the inner product of chi and psi is the product over all n of the Cn's. So let's consider two cases. The inner product is non-zero or the inner product is zero. In the first case, I'm going to show you that the two Hilbert spaces are the same. To make the product be positive, so the Cn's are all numbers between 0 and 1, real numbers between 0 and 1. If it's positive, the Cn's rapidly converge to 1. Now, by acting with the algebra O on psi, we can change any set of Cn's at will, because we can do anything we want to finitely many of the states. So because our algebra consisted of polynomials in the p's and x's, well, polynomials in p's and x make an algebra that's big enough to do whatever you want on one factor of the Hilbert space, and even on any finite set of factors. But you can't do whatever you want on infinitely many factors. So with our algebra is big enough that we can change chi n for finitely many n however we want. So we can replace any finite set of the Cn's by 1, or by numbers arbitrarily close to 1. Since the product is converging to a positive number, that means that the Cn's are rapidly approaching 1. And there are finitely many of them that are not too close to 1, but we can change them by acting with our small algebra. So in other words, in case 1, there's a finite set of elements of the algebra such that the inner product of chi with O sub r acting on psi approaches 1 as r goes to infinity. So that means that chi is in the Hilbert space of psi. And this 9 should be a 0. Of course, the argument is symmetrical in psi and chi. So the same argument would prove that psi is in H chi. So the two Hilbert spaces are the same. In case 2, well, there might be, the inner product might be 0 for a stupid reason that finitely many of the C's are 0. If that's true, we can remove those zeros by changing chi by the action of our small algebra. If infinitely many of the C's are 0, then our Hilbert's, well, let's assume that isn't the reason that this inner product is 0. So if the reason the inner product is 0 isn't that there are finitely many bad C's, instead, the bad case is that the product vanishes because the C's don't converge very fast to 1. That means the vanishing wouldn't be changed by changing finitely many of the C's. So chi is orthogonal not just to psi, but to any O psi where O is in the small algebra. So if the reason for vanishing isn't just finitely many C's vanishing, then chi is orthogonal to the whole Hilbert space H psi built on psi. So the two Hilbert spaces actually are orthogonal to each other in this case. So our two Hilbert spaces either are the same or else they're orthogonal to each other. So for states of this kind, there are only two options. Chi is in the Hilbert space built from psi, or it's orthogonal to that Hilbert space. In short, for H psi and H chi to be the same Hilbert space, we require no relation between psi and chi at all for any finite set of modes, but for large n, psi and chi must coincide asymptotically. I illustrated this for the case in which psi and chi are diagonal, tensor products of vectors in the individual HNs. But that's not important unless one aims to give a rigorous proof, which I'm certainly not going to try to do. Any questions here? We're about to go back to field theory, so this is a good place to stop for questions. Now let's go back to quantum field theory in curved spacetime. The easiest case is a closed universe. I've drawn a 1+1 dimensional closed universe. For high energy modes, we know what to do to very good approximation. Modes of very short wavelength can be separated to positive and negative frequency with very small uncertainty. In fact, this uncertainty is exponentially small at high energy, where high energy means high energy compared to 1 over the radius of curvature of the universe. For low energy modes, we have no idea what to do. In general, there's no sensible approximation to a preferred state. So to pick a candidate psi, we use any state at all for the low energy modes, and we use a separation in positive and negative frequencies for the high energy modes. Because the universe is closed, there only are finitely many modes below any given high energy cutoff. So to good approximation, we know what to do for all but finitely many modes. Since we know what to do for all but finitely many modes, we're in the good situation. There isn't a preferred psi, but the Hilbert space H psi that we construct does not depend on psi. An asymptotically flat spacetime is almost as good. For any mode near spatial infinity, we have a good separation in positive and negative frequencies because the spacetime is asymptotically flat. In other words, near spatial infinity, the world is flat and you know what are positive and negative frequencies. We also know what are positive and negative frequencies for modes of sufficiently short wavelength because the spacetime is approximately flat at short distances. So the only modes where we don't know what to do are the ones that are in the region where the space is curved and also have a wavelength comparable to or greater than the radius of curvature. But there only are finitely many of those modes. In other words, the bad modes are the long wavelength modes in the interior. So we're back in a good situation in which we know what to do, or we almost know what to do for all but finitely many modes. So again, there's a preferred separable Hilbert space that we can define with a good treatment of all but finitely many modes and any treatment of the others. So in each of these cases, you can also construct an algebra of observables, AW, for each spacetime region, W. So, well, I wrote it actually here in terms of bounded functions. You take the field phi and you smear it by a smearing function f. And then to get a bounded function, you take the exponential of I times the smeared field function. So we get this u sub f. And then we can construct a Vinomin algebra of bounded operators supported in W. Incidentally, it's traditional to use Vinomin algebras here, but I'm not entirely satisfied. It's the best thing to do. Well, maybe we'll get to that later. So the Hilbert space, of course, depended not just on this bounded region W, but on what was outside. But the algebra AW, and informally the space of possible density matrices of region W, doesn't depend on what's happening outside of W. That's because the underlying separation of high energy modes into positive and negative frequency can be made locally. And this separation in region W doesn't depend on what's happening outside. So all the considerations that go into describing quantum mechanics in W and operators that act there are local in W. What I really think, instead of the von Neumann algebra, certainly for free field theory, you should forget about taking bounded functions, just look at smeared functions of phi, or even don't smear, and just look at the operator product algebra. So certainly for free field theory, describing the operator product expansion of the field phi is more illuminating, or most illuminating for most physicists. And that exists in W irrespective of what's happening outside. And then it gets represented in the Hilbert space we constructed, no matter what there was outside. But the local algebra, regardless of what version of local algebra you want to talk about, it doesn't depend on what's happening outside. That'll be important in a little while. Now, this is all well and good, but let me tell you something that does not work. Consider a space-time that's not closed. It goes off to spatial infinity. And it's time independent, even at spatial infinity. In that case, as far as I know, there is not a natural way to construct a Hilbert space for a quantum field in M. An example is cosmology. Assume the universe is open and the stars and galaxies go out to spatial infinity. Or maybe even wilder things happen as in a multiverse. Maybe what happens at big distances is worse than stars and galaxies. In that case, I do not believe we have a reasonable Hilbert space for a quantum field in a cosmological spacetime. The complications are affecting infinitely many modes of the quantum field. To describe a seed vector psi that we could use to construct a separable Hilbert space, we need to provide a ridiculous amount of irrelevant information about what's happening at infinity. And logicians might tell you you can't do that, but even if you could, you wouldn't want to try to do it. However, a local observer who's limited to measurements in a compact region W does have a natural algebra of some kind and a natural, well, informally, a natural space of density matrices. To this observer, the universe might have been closed, so the algebra and the space of density matrices should exist. The algebra doesn't depend on whether or not the space-time was closed up outside W or how it was closed up if it was, so it's natural and unique. The most obvious version of that might be to think of the operator product expansion, which you'd make in the region W without knowing what is outside W. So I should warn you, I've been a little cavalier. The rigorous statement is only that the observer in region W has a well-defined algebra of observables. The phrasing of density matrices is heuristic. Well, I wrote here, I'll explain the rigorous version at the end, but that was too optimistic, I'm afraid. I'll say a few words, but I'm not satisfied with them. Now, since this situation may be confusing, I'm going to explain a simpler situation.
So, I have a question. I'm a bit confused. So are you advocating that in this case, actually, we shouldn't even try to think about the Hilbert space, but we should try to do the theory in terms of this algebra instead? Is this the message?
I believe so, something like that. I don't think we have any choice. I don't think there's a sensible Hilbert space.
Okay.
For in a closed universe or asymptotically, instead of asymptotically flat, it could have been asymptotically anti-de Sitter. That's just as good. In a closed universe or with some good control at infinity, there's a Hilbert space. When that isn't the case, we're not in that situation. And I don't think there's a Hilbert space, a sensible one.
Okay.
I'm going to describe a simpler situation that's actually rather analogous. Forget curved spacetime and just consider quantum field theory at non-zero temperature. So is there a good Hilbert space for describing quantum field theory in non-zero temperature? Well, in finite volume, there's no trouble. We had a good Hilbert space that contains states of all energy. Regardless of the temperature, the energy is finite in finite volume. And the thermal states at finite temperature are in the Hilbert space we described. In infinite volume, there is a problem. There isn't a separable Hilbert space that contains all the typical states of the system at non-zero temperature, since fluctuations occur throughout the whole infinite space. So it looks like we need to work in a non-separable Hilbert space H hat if we want it to contain the typical excitations of a system in infinite volume at temperature non-zero. And to get down to a separable Hilbert space, you'd have to try to give a seed vector that would have to be a typical vector in the Hilbert space. And that's a ridiculous thing to do, and logicians might tell you you can't. Almost every vector is typical, but to try to describe a typical vector wouldn't be much fun. And you wouldn't be interested in a Hilbert space that was defined using the details of a typical vector, even if you could do it. So there definitely isn't a reasonable, well, I'll describe later what you should do instead, but there isn't a reasonable separable Hilbert space that contains all the thermal fluctuations in infinite space. Similarly, for the infinite spin system, here's a spin system on a lattice. I explained to you that if you have a Hamiltonian, then at zero temperature, you can make a nice separable Hilbert space that contains all the states you want to talk about. But at non-zero temperature, you can't. At non-zero temperature, it looks like all the states in that ridiculous, or it looks like you need to go back to an unseparable Hilbert space to describe the physics at non-zero temperature. But there's something you can do to fix it. There's a simple device to avoid this and work in a separable Hilbert space. It's called the Thermo-Filled Double. For an ordinary quantum system with Hamiltonian H and Hilbert space curly H, to construct the Thermo-Filled Double, you add a second copy H prime of H with the same Hamiltonian acting on it, and you work in the tensor products. I wrote H times H prime, but this should have been the tensor product. If the Hamiltonian H has energy eigenstate psi I with energies EI, the Thermo-Filled double is this pure state, 1 over the square root of the partition function to normalize it, times the sum of I in one system times I in the other system, weighted by e to the minus beta times EI over 2. The point of this formula is that the density matrix for system H, where you integrate out H prime, is simply a thermal density matrix. In other words, if you do a partial trace over H, for each I, there's only one state in the second system that's excited. So the partial trace over the second system will just give you the sum of projectors onto I, each weighted with the square of this coefficient, which is the appropriate thermal factor for the state I. So this Thermo-Filled double has the property that the induced density matrix on H is the desired thermal density matrix. So the Thermo-Filled double is trying to be a purification of a thermal density matrix. So the only problem is that we want to interpret the Thermo-Filled double in a separable Hilbert space. We don't get that for free because for an infinite system, the sum of I went over all the energy levels of the infinite system, of which there were uncountably many. So we still want to see that we can interpret the Thermo-Filled double in a separable Hilbert space. In quantum field theory, as I think you probably all know, you construct the Thermo-Filled double by a path integral in a strip m times I, where m is space and I is an interval of width beta over 2. So the path integral in this space gives a vector in the tensor product of 2 copies of the Hilbert space on m being the spatial manifold. And that state is the Thermo-Filled double. And the statement that the partial trace over one factor is a thermal density matrix would the exhibit proved in field theory by gluing this onto a second copy. I wish I had that drawn. And tracing over one copy, and then you'd end up with a strip of width beta. And that would construct a thermal density matrix for the original Hilbert space, the original copy. So the Thermo-Filled double psi is a concrete seed state, which by this definition started its life in the tensor product of 2 uselessly big non-separable Hilbert spaces. But what we gained by going to the Thermo-Filled double is that we do have now a concrete seed state. For a single copy, we didn't have a concrete seed state to use in constructing something manageable. What I've tried to explain throughout this lecture is that whenever we have a state we know we like, starting from that state with a reasonable algebra of observables, we can make a reasonable Hilbert space. In the thermal problem, for a single copy, we didn't have a reasonable state because every state had complicated fluctuations off to infinity, and there was no typical state to talk about. The Thermo-Filled, by going to 2 copies, we do have a concrete seed state. So now we can imitate what we've done throughout. We consider an algebra A0 of observables that we know we want. For example, in the spin system, this would be the operators that act on only finitely many spins in the original system, in the first copy. In field theory, we could take a simple class of functions of the field phi in compact regions of spacetime, again on the first copy, the copy we're actually interested in studying. But importantly, we take the simple algebra to act on one copy, not on the second copy, because the goal of the exercise is to study the thermal physics of one system. The second system was introduced because otherwise we couldn't get down to a reasonable Hilbert space. So now we define a separable pre-Hilbert space H0 that consists of all states obtained by acting on the seed state psi, the Thermo-Filled double, with operators in these small algebra. As usual, we complete this to a Hilbert space H, still separable. Likewise, we complete A0 in the usual way by considering limits of sequences of operators on H, whose matrix elements all have limits. This gives an algebra of observables A at temperature T. We've gotten then a standard-looking separable Hilbert space H in which to study thermal physics at temperature T. There's only one thing that's odd. The algebra A is of an unfamiliar kind. A does not act irreducibly on H. It cannot, since it commutes with the second algebra A prime, that's actually isomorphic to A, that could be defined similarly, starting with simple operators on the second copy. But more than that, typically this construction leads to an algebra that cannot act irreducibly on any Hilbert space. Algebras that have no irreducible representations. They're called Vinomin algebras of type 2 or type 3. So a Vinomin algebra that can have an irreducible representation is type 1. But this Thermo-Filled double will typically lead to a Vinomin algebra of type 2 or type 3. Really typically type 3, but I'll tell you how to get type 2. So what happens can be illustrated with very simple spin systems. Well, the blue diamonds are meant to be the qubits we're interested in studying. But to study them at non-zero temperature, we introduce a second copy, which are the red diamonds. And very simple Hamiltonians are going to give us complicated Vinomin algebras. The simplest example is to take the Hamiltonian to be 0. I think you'll agree that that's the simplest Hamiltonian of all. The Thermo-Filled double, okay. What's the Thermo-Filled double? Well, the Hamiltonian 0 doesn't couple the different qubits. So we could construct the Thermo-Filled double just for the blue qubit and one part in a red qubit. What would it be? Well, it's an equal sum over all states. The two qubits are in the same state. And they're supposed to be weighted by the exponential of minus beta over 2 times the energy, but the energy is 0. So all states are equally weighted. So the Thermo-Filled double just means that this blue qubit and this red qubit are either both up or both down, maximally entangled. And the same is true for each qubit pair. Each blue qubit is in a maximally entangled state with the corresponding red qubit. So the Thermo-Filled double state is just a completely entangled state of the two systems, where the nth qubit in the first system is completely entangled with the nth qubit of the second system, and then we divide by a normalization factor so that the state psi is a unit vector. And we adjust z as the number of qubits goes to infinity so that psi remains normalized. Now let A and B be elements of the small algebra, which I remind you are operators that only act on finitely many spins of the first system. Define a function f of A, which is the expectation value of the operator A in the state psi. Well, here are a couple properties of f of A. One is it has a thermodynamic limit. That's obvious because when we add new spins to the system, the operator A doesn't act on them. And the normalization factor is adjusted so that when we compute this matrix element, the new spins just cancel out. The second obvious fact is that if A is the identity, then f of A is 1. That's obvious because psi is normalized. A third fact, which is only slightly less obvious, is that f of AB equals f of BA. That's because this Thermo-Filled double has the property that f of AB is that, see, A and B are operators that only act on finitely many qubits, let's say the first n. And then you could see with this state, f of AB is just the trace of the product AB in the finite dimensional Hilbert space of the first n qubits, divided by a constant, which is such that the trace of the identity is 1. So f of AB equals f of BA. And last property is that, sorry, I left out the f here. It should have been f of A dagger A is non-negative for all A. Now, by continuity, these properties are all true when we take limits and allow AB to be in the limiting algebra A, the completion.
This commuting property is satisfied precisely because H is 0, correct?
Yes.
Okay, thank you.
This trace property, f of AB equals f of BA. The Hamiltonian has to be 0 to make that true. Everything else I said is true for other Hamiltonians. But this f of AB equals f of BA is only because the Hamiltonian was 0. So therefore, we're going to get a very special von Neumann algebra. Now, unless you've studied strange von Neumann algebras, you've never run into an algebra with these properties. Since f of AB equals f of BA, the function f of A is the axioms of a trace. But it's not actually the trace in any Hilbert space representation of the algebra. A giveaway is that the element 1 has a well-defined trace. The von Neumann algebras you're most familiar with are the algebras of all bounded operators on a Hilbert space. But then you can try to define a trace, but obviously the trace of the identity is infinite because the Hilbert space is infinite dimensional. And there's no way to renormalize the trace to make the identity have a well-defined trace. So the usual algebra of all bounded operators on Hilbert space has the property that you can define a trace which is well-defined for a certain subset of operators, the ones that are said to be of trace class, but it's not defined on the whole algebra. That's what I said here. In the usual algebra, you can try to define the function trace of A in the Hilbert space, but it's not defined for all A, and the f of 1 is infinity. From the H equals 0 Thermo-Filled double, we've got an algebra of exotic type called a Vinomin algebra of type 2-1. It has a trace defined for all elements of A. That's very different from the algebra of all operators on Hilbert space. It does not have any irreducible representation in Hilbert space. Its representation on the space H that we constructed from the Thermo-Filled double is highly reducible since it commutes with the operators on the second copy. By taking more and more operators on the second copy, you can reduce this Hilbert space representation into smaller and smaller pieces, but you never get to anything irreducible. Any questions on that? So if you look at my lecture notes, I described this algebra, but I didn't do what I think I should have done, which was to motivate it the way I've done today. Now, with other very simple Hamiltonians, you can construct the other important von Neumann algebras. The next simplest case is the Hamiltonian that's a sum of single spin operators that are all the same. For example, this one. So each HI could be just this matrix whose eigenvalues are 1 and 0. Then the Thermo-Filled double has the property that the ith pair of spins is decoupled from all the others and is entangled fully, but not maximally in this state. So then we can do everything we said before and define this function f of A that has a thermodynamic limit, but it's not a trace. So this algebra, again, doesn't have irreducible representations because it commutes with the algebra acting on the second copy. And it's a new algebra different from the one before because it doesn't have a trace. It's called an algebra of type 3 lambda, where lambda is e to the minus beta.
Just to be clear, this argument doesn't say that the algebra doesn't have a trace. It just says that the F you chose is not a trace, correct?
I did not prove there isn't a trace.
I see.
But people who study von Neumann algebras, I think this is attributed to Alain Kahn in the 1970s. So Alain Kahn proved that these algebras type 3, what I've just defined is called an algebra of type 3 lambda. Alain Kahn proved that they're different from each other for lambda between 0 and 1, and are also different from the type 2-1 algebra that we described before. Don't have traces. And well, when people say he classified von Neumann algebras, the other ones he introduced were of type 3-1, which I'm about to do, and there's another limiting case of type 3-0, where you roughly try to take lambda to 0. But anyway, you're completely correct. I didn't prove this algebra doesn't have a trace, but that's a standard fact about von Neumann algebras. I have no idea how it's proved. Now, for practically any more generic Hamiltonian, this construction gives what's called a type 3-1 von Neumann algebra. The definition is basically, well, the definition of such an algebra is basically that for any state psi, the corresponding modular operator has a continuous spectrum consisting of all positive numbers. So this one, for this vector that we got, the tensor product of all these, if you work out the modular operator, its eigenvalues are powers of lambda, positive and negative powers of lambda, integer powers of lambda. A type 3-1 algebra, Kahn's definition is that for any state, the modular operator has a continuous spectrum consisting of all the positive numbers. So we could actually get that. We could actually write a trivial Hamiltonian which has that property. Instead of assuming, where did I write it? Instead of assuming that each spin has the same Hamiltonian, if I just take single spin Hamiltonians, but different ones for different spins, in a way that doesn't have to be very generic, but is a little bit generic, then we'd get an algebra of type 3-1. Now let's go back to quantum field theory. In Rindler space, we were able to compute the modular operator of the vacuum state. It was the exponential of -2 pi times the boost generator k. That has a continuous spectrum consisting of all positive numbers. Moreover, states with any positive eigenvalue of delta can be constructed from perturbations that are arbitrarily close to the edge of the Rindler wedge. Since every state looks like the vacuum at short distances, it's believed, I don't actually know to what extent it's rigorously proved, that the modular operator of Rindler space has continuous spectrum, 0 infinity, for every state, and hence that the algebra is of type 3-1. The thermal nature of the Rindler density matrix means that the analogy with the Thermo-Filled Double is reasonable. In other words, I described the Thermo-Filled Double for a Hamiltonian where the subtlety came from what happens at large distances. Here, the Hamiltonian is k, and although you could worry about large distances, k grows at large distances, which tends to cut off thermal fluctuations. The important subtlety here is near the edge of the Rindler wedge, where k goes to 0, and the thermal fluctuations are out of control. So there is a reasonable analogy between Rindler space and the thermal system, with the edge of the Rindler wedge corresponding to large distances in the thermal system. So for the Rindler space, we had this exact answer, which exhibited a kind of thermal description. But the Riesz-Schlieder theorem tells us that something somewhat similar is true in general, with the degrees of freedom inside completely entangled with those outside. Now consider any compact spatial region W in its domain of dependence D. Near the corner, D looks like a Rindler wedge. So for very short wavelength excitations near the corner, D is indistinguishable from Rindler space. It's believed, but I believe not vigorously proved, that the modular operator of region D has the same continuous spectrum as Rindler space for any state, because it looks like Rindler space near the corner. So the algebra is again of type 3-1. But I think more naively, it should be of type 3-1 because I believe that's the generic answer for almost any Hamiltonian for thermal systems in infinite volume. In other words, I think the burden of proof would be to get one of those more special algebras of type 3 lambda or type 2. A more elementary reason to at least suspect that the algebra of a region in quantum field theory is not of type 1, and thus does not have irreducible representations, is the universal entanglement entropy of a region. As I said before, I think in one of the lectures, if the algebra of regions 1 and A and B were of type 1, then you could have a tensor product state psi A tensor psi B with 0 entanglement entropy. And of course, you could also have a non-zero but finite entanglement entropy. Instead, in type 2 and 3, a divergence of the entanglement entropy is built into the structure of the algebra, which is what we have in quantum field theory. And then I guess here I confess to the fact that density matrix is really a type 1 concept. A type 1 algebra has an irreducible representation on a Hilbert space, and a density matrix is a non-negative Hermitian operator on that Hilbert space of trace 1. In type 2 or type 3, there's no notion of a density matrix. The closest analog is a state on or of the algebra. What people who do von Neumann algebra say is that a state is a complex valued expectation, A going to f of A, which is positive on all A dagger A. In particular, with psi being the Thermo-Filled Double or any other state in the Hilbert space, H that we constructed starting with the Thermo-Filled Double, the expectation in the state psi is such a state. I'm not totally happy with the way, I'm not an expert, first of all, on what people say vigorously about this situation in curved spacetime, but I'm also not totally happy with it. I think one should build in the operator product expansion so that the only kind of state you'd be allowed to talk about would be those with the correct short distance singularity. Whereas what I see people doing is defining states more abstractly and then worrying about whether the short distance singularity is correct. I would prefer to build in more structure so that the only states you can talk about have the correct short distance singularity. I guess there's one more thing I'll tell you about a type 3-1 algebra. any two Hilbert space representations of such an algebra are isomorphic. That wasn't true, for example, for type 2.1, but it is true in type 3.1. Going back to quantum field theory in a space-time that's open and time-dependent, the sense in which quantum field theory makes sense in such a space-time is that you can define algebras, AW, associated to such regions, obeying various natural axioms. For example, for space-like separated regions, the algebras commute. And quantum states in such a region are at least roughly states in the algebraic sense. Such an observer doesn't have a pure state, and the idea of a density matrix is also oversimplified. As I've told you, though, I'm not completely satisfied with the language I used in describing it. Because, well, again, I'm not an expert in what people have said, but what I see people saying is in a language where the notion of a state is more loose than you would like. I hope it will be done correctly. Well, I would say more correctly with the operator product expansion built in. Anyway, that's what I have to say for today.
Thank you very much. And now we're open for questions.
Well, Edward, when you said your last slide, can you give an example of some particular space-time where this program was carried out to some sufficient explicit answers?
You mean the program I said I wasn't 100% satisfied with?
No, but yeah. Somewhere where these algebras were constructed and states were constructed, like can we take some particular state, space, time for which the usual language doesn't work, while this language works and gives something sensible?
Well, yeah, I can suggest there are two references I've looked at. So one was a paper by Graham Siegel, and I haven't looked at it for more than 30 years. It was about free fermions in 1+1 dimensions. He did, see, in that case, if you picked it, of course, you could pick a metric, which would make it a cylinder, a flat metric. I now can't see myself, so I'm not sure if you're seeing what I'm trying to pantomime, a flat cylinder. But if you pick a flat metric on the cylinder, you're in a time-independent situation, and you want to, then it's obvious you can construct a Hilbert space by minimizing the energy. But Graham wanted to approach it somewhat more differently, more in the spirit of what I said. Picking any, making any choice of creation and annihilation operators, which is standard at sufficiently high energies. And he gave rigorous proof in that setting, but it was only for chiral fermions in 1+1 dimensions. There's also a short book by Robert Wald called Quantum Field Theory in Curved Spacetime. And he definitely gives what he claims is a rigorous account of quantum field theory in curved spacetime. And to be honest on this, I would trust him more than I would trust myself. So I'm not skeptical.
No, but was it for which spacetime? Because for the spacetimes, you described two kinds of spacetimes which you said were okay, namely the ones which were asymptotically flat or compact. And for those things, it sounded very convincing. But now you said that for spacetimes which are not okay in that sense, we can still try to do quantum field theory in this algebraic sense. So I was wondering if there is any explicit example of such a space-time where things did calculations and so on.
Well, I recommend looking at Robert Wald's book.
Okay.
As I said, it's based on this approach where a state with the correct short distance singularity is what he calls a Hadamard state. I'd prefer to discuss it in language where you're only allowed to talk about Hadamard states, because the short distance singularity, the OPE, should be built into the definition of what you meant by the algebra. So that isn't done. So I'm not 100% sure I'm satisfied with the way it's approached, but as I said, I trust him more than I would trust myself on statements of rigor about this particular question.
Zor, I think you're next.
I had a small question about the Thermo-Filled Double.
Yes.
So one way that I can understand what it means is if I start in compact space, I can prove that the entropy as a function of the energy does not grow faster than an exponential of the energy, and therefore the everything nicely converges. On the other,
if you want to prove that thermodynamic functions converge, you can do thermodynamics in finite volume in the standard Hilbert space, and then take limits.
yes,
My discussion applies if you want to actually give a Hilbert space in which the standard infinite volume thermodynamics makes sense.
right. So my question was about the convergence of the Thermo-Filled Double state for the Hamiltonian 2 pi k. Since I don't know how to put it in compact space and prove convergence, how do we do that?
The Thermo-Filled double state for you're talking about Rindler space?
Yes.
In that case, the Thermo-Filled double state is just the vacuum of the original theory in Minkowski space.
Well, yeah, in that case, we have another argument. But more generally, if we want to study e to the minus 2 pi k as the density matrix, quote unquote.
Well, density matrices are problematical. But for the modular operator, the Thermo-Filled double is always going to be the original state you started with in the original theory.
Yes. Yeah, in the event that it comes from some well-defined state in the original theory, I can understand why it's well-defined. Thanks.
Okay.
Hagu?
I have a very naive question. Could you say a few more words about why the non-separable Hilbert spaces are very big, or why we don't like them so much?
Well, I can tell you, you've never, I strongly suspect you've never had any physics done in an unseparable Hilbert space.
Okay, so it's just like a fact about the systems we deal with in physics. There's nothing intrinsically bad or anything about them.
Well, I think you'd be hard pressed to find math theory too.
Okay.
I think mathematicians have discovered that neither math nor physics is usually done in unseparable Hilbert space. I'm less confident about math than I'm about physics. Maybe there's some branch of mathematics where people work in unseparable Hilbert spaces. I bet it would need to prove crazy counterexamples or something.
But in physics, it has to do with this fact that at some point you only want to turn over a finite number of spins or apply things in a finite rate.
I think it's because physics is normally, when we consider infinite systems with infinitely many degrees of freedom, it's somehow a limit of a system with finitely many degrees of freedom. So there's a good language where you only talk about finitely many degrees of freedom. But what I showed you was that in thermodynamics, although you can find a language that involves only finite, that involves a separable Hilbert space, it involves these crazy algebras. But okay. When you learned about spontaneous symmetry breaking, you had, let's say, a field valued in a two-sphere. It could point in any direction. They told you not to construct a Hilbert space with states where it points in all possible directions. Those are orthogonal. Those Hilbert spaces are orthogonal to each other, and you can do complete physics in just one of them. It's useless to try to take the direct sum of all of them, which would have given a non-separable Hilbert space.
Yeah, I agree. It was just a naive question, as there was something obviously bad about such big Hilbert spaces. Or as a physics thing, I agree that it makes sense to talk about this.
I'm not really offering a money-back guarantee that nobody will ever say anything useful in a non-separable Hilbert space. I'm only saying that I don't believe it's happened in physics, and although I'm less sure, I'm reasonably skeptical it's happened in math.
Okay, yeah, thanks.
So I also have a question a bit about the big picture, because here you're emphasizing a lot this Hilbert space description of quantum field theory. And here, as in the Bootstrap, we tend to think of quantum field theory just as a set of correlation functions that obey some consistency conditions.
Yes.
So I wonder if that approach would be more useful in this context also.
Well, your correlation functions are effectively in a preferred state, the vacuum usually. So if you're in curved space-time, you wouldn't have the preferred state. You could talk about correlation functions in any state. So
I wonder if we could define like a set of correlation functions that they would be self-consistent, and well, that's
well, you could you can
don't have to talk about state. I don't.
You see, if you do have a Hilbert space, you could discuss the correlation functions in any possible state. But for free field theory, you could talk about any possible coherent state rather than any possible state. That would be a meaningful notion. But, or am I wrong? Sorry, I'm worried. I was speaking off the cuff. I don't think I thought about that carefully enough. I'm not sure that makes any sense. It's just a question. I'm not making a claim. What Wald would tell you would be to talk about, okay. In Wald's formulation, you have this algebra, and then you talk about Hadamard states, which really, a Hadamard state would be a set of correlation functions that obey the right short distance singularities. You can talk about all possible correlation functions in a given region that obey the correct short distance singularities. That would be, I ended up telling you that, as far as I know, in a completely open space-time, that's all you can do, really.
Right.
But it wouldn't have very bootstrappy flavor because it's not highly enough constrained, I don't think.
Can I press you a bit more, Eder? So, for example, let's take a concrete example. Like, okay, people do calculations in quantum field theory in expanding universe, either FRW or maybe some more complicated inflationary backgrounds. So those backgrounds, they look like the ones that you wouldn't classify as okay.
Some are okay, some not. So, for example, in the inflationary universe, when people are generating cosmological perturbations, they do have a preferred state they start with. I forget if it's called the Bunch-Davies state.
The Bunch-Davies, there are good physics arguments which explain why there's some relaxation of states. So does this formal theory have anything to say about why the Bunch-Davies vacuum is really like physically preferred? Because that we believe that there are good physics reasons to believe that it's a good state.
Well, in that case, because of the exponential expansion, every state approaches that after a while. So that's the good
exponential. Even like in a normal FRW, I think it's also a reasonable choice of a state in presence of interactions.
What did you mean in FRW?
In a usual radiation or matter dominated expanding universe, that would also be a reasonable state to consider.
What state do you have in mind there?
Excuse me?
I don't know what state you have in mind in FRW. I literally don't.
Well, I meant a state which has a kind of, okay, let's call it Bunch-Davies-like, which has short distance modes in the vacuum state.
What do you mean by vacuum state? I think FRW is a good case where there isn't a preferred state.
Well, there isn't the preferred state, but I think maybe I'm remembering it incorrectly because it's been a long time since I looked at this type of things. But if you do a free theory, there is definitely not a preferred state. But if you do a theory in presence of interactions, then I think there is some notion of if there are some interactions which act sufficiently fast compared to the expansion of the universe, then I think one could make statements of the kind that the state of the quantum field will be attracted to some state which will then evolve, somehow adiabatically. So there's going to be some transient period.
I don't think there's anything like that. All you can say is that under some conditions you can expect it to thermalize, but thermalization isn't a preferred quantum state. And that would actually mix the two problems we discussed. One is the open, expanding, non-stationary universe, and the other is the thermal system in an infinite volume. The case would be worse than anything I discussed. If it's thermal in infinite volume, you would try to improve the situation by doing a Thermo-Filled Double. But because it's expanding, you wouldn't know how to do the Thermo-Filled Double either. Well, you could assume local. Okay. I think the only simple thing you can do in practice is to assume local thermal equilibrium and compute on that basis. I'm skeptical there's any true quantum function calculation that you can do in FRW. I could be wrong. I don't claim I could be totally unaware of something significant that's been done.
Well, but people do calculations, so I'm
Well,
confused. Yeah.
What people usually do is just to assume local thermal equilibrium and do calculations that only depend on thermodynamics. You can do that. That's not a computation of quantum correlations beyond the extent to which they're predicted by thermal equilibrium. You certainly can say that one thing which is certainly true is that if at some time an FRW universe is to good approximation in local thermal equilibrium, then that remains true at later times, except for possible effects of phase transitions. Standard cosmology is only based on that. It's not based on any real quantum calculation.
Yeah, that's true. There's probably not really any need for that.
Okay, perhaps can you maybe this is the answer to my question already, but is there like a standard problem that would be the challenge for this type of question? What would be the simplest setup that would already be? What would be the sharp question? One example that we would like to solve and we don't know because of these obstacles.
I don't have a specific question in mind, to tell you the truth. I'd like to, I want to mention something that was done in paper by Juan, and I'm afraid I don't remember who in a second. But before mentioning that, I just want to say something that doesn't work. So for FRW, as far as I know, with an FRW Big Bang, you can't define a preferred state. But you could try to define a preferred density matrix, which you could imagine doing as follows. Try evolving back in time, but then go into complex time, go around the singularity and come back to real time. And if that worked, maybe you could have made a distinguished FRW density matrix. But it doesn't work generically. Well, I think there's a paper, I think there's one of Juan's papers which involved the fact that in a conformal field theory that actually does work. And you can make a distinguished FRW density matrix. But maybe it's more special than generic FRW. I'm not remembering how general it was. But at least in a nice situation where the analytic continuation made sense, it was possible to construct a density matrix, though not a preferred state.
Any other questions? Not, let's thank Hilbert again.
Sure. See you at 9 Mountain Time tomorrow.
Yes, see you all tomorrow.